Before I introduce our speaker this evening, I'd like to thank the Simons Foundation for both encouraging us and making it possible for us to mount these very exciting lectures, the Great Thinkers series, and in fact most all the series. Great thinkers think about great ideas, and while Descartes may have begun his existential investigations in 1644 with the notion of cogito ergo sum, I think therefore I am, and John Locke referred in his essay concerning human understanding to the ultimate essence underpinning everything as the material substratum, modern scientists and philosophers want not only to know that they exist and of what they exist, but why they exist. Why, for that matter, does anything or everything exist, if it does, and what is it all about? In other words, they want a theory of everything, a grand unified field theory uniting the laws of the micro and macro universes, which Einstein was working on until his death, but was unable to find. Some of the people best equipped to mine that field, if you'll excuse the pun, are the cosmologists and mathematical physicists who toil in the abstract worlds of relativity and quantum mechanics and speak the language of mathematics, which seems to be the language which many of the most important existential and universal questions in which they are written. Edward Witten, who will deliver his talk entitled String Theory and the Universe this evening, is uniquely qualified to speak on this subject. In addition to being one of the world's most gifted mathematical physicists, he was also a history major in college, so he brings special perspective to his talk about origins and material substrata this evening. He has earned so many prizes and distinctions for his work that there is not time here to mention but a few. Suffice that Professor Witten is the Charles Simoni Professor of Mathematical Physics in the School of Natural Sciences at the Institute for Advanced Study, a winner of the Fundamental Physics Prize, a $3 million prize recently established by Yuri Milner to honor the greatest physicists in the world, a Fields Medal, the highest award given in mathematics, which few outside the field of pure mathematics have ever won. Hi, Jim. A MacArthur Fellow, a winner of the Dirac Medal, the Einstein Medal, etc., etc. Edward is the go-to person in supersymmetry and string and M theory, the person everyone wants to hear from for the most advanced thinking on these subjects. It is indeed our good fortune to have Edward Witten here at Hunter College tonight on behalf of the Writing Center, speaking to us about one of his favorite subjects, string theory and the universe. Edward Witten.
Thanks, Louis, for the kind introduction and for inviting me here. And while I was, in the last couple of moments, while I was waiting for this event to begin, I realized to my chagrin that I've made a small error in the title page, which is that I've misstated the name of my institution, which is actually the Institute for Advanced Study, not Studies. So I'm actually going to begin this lecture by telling you about particle physics in general and how 20th century physics developed, and then we'll get into our title, String Theory and the Universe, in the latter part. So first of all, well, I was educated as a particle physicist, but what is that? If you're not in physics, particles sounds like it might be a specialized aspect of the world. What particle physicists are really interested in is understanding the laws of nature. The laws that are at work in all the sciences, biology, chemistry, astronomy, wherever we look around us. The reason that 20th century physicists gave the name particle physics to this endeavor is that understanding elementary particles turned out to be an important part of trying to understand the laws of nature. So we see a lot of things in the world around us, for example, light waves. But according to quantum mechanics, if you look more closely, light waves are made of little packets of energy, which are called photons. The photon is one of the elementary particles. So that's an example of something that 20th century physicists came to interpret in terms of particles that was not understood as being made of particles before the 20th century. Similarly, matter, when studied more closely, is made of atoms, and atoms are made of protons, neutrons, and electrons. And when you look still more closely, the protons and neutrons are made out of smaller things called quarks. As far as we know today, the quarks and electrons are indivisible, and they are some of what we call elementary particles. Now, one of the experiments that got particle physics started, or well, not just particle physics, modern physics. Thank you. So, modern physics got started in large part when Ernest Rutherford discovered the atomic nucleus in a famous experiment in which he bombarded atoms with energetic particles. At the time, an atom was envisaged as being like a little ball of jelly. And Rutherford expected that his highly energetic particles would pass through it like a bullet passing through a sheet of tissue paper. And was quite surprised instead when he discovered events where the particle was scattered through a large angle. Sorry, I think I stepped away from the mic for a second, so I'll just say that he expected the energetic particle to pass through the atom like a bullet through a sheet of paper, and was surprised to discover that there were events in which the highly energetic particle was actually scattered through a large angle. That was the discovery of the atomic nucleus, a hard kernel inside the atom that was so hard that it could scatter the fast-moving bullet. Now, Rutherford made this discovery with what in his day were regarded as high-energy particles, though we would not think of them as high-energy particles today. But he did not have any method to accelerate the particles that made up his beam. He used a natural radioactive source. So, for example, an old-fashioned radio watch, the radioactivity means that the atoms are emitting particles that have more or less the energy of the particles in Rutherford's beam. So, to give you an idea of what the yardstick is, if I measure energy in units of an electron that would come out of a flashlight battery, that would be called 1 electron volt. So compared to the energy of an electron in a flashlight, the energy of the alpha particles in Rutherford's beam was 1,000,000 times larger. 1,000,000 electron volts is abbreviated MeV. So the next one is a GeV, a particle physicist's unit for 1,000,000,000 electron volts. And I'll give you another explanation of what a GeV is in a moment. Rutherford's experiment was done at roughly the same time that Einstein was learning that E equals mc squared. And another way to say what is an MeV or a GeV is that an MeV is basically mc squared for an electron, and a GeV is mc squared for a proton. And the next one is a TeV, that's 1,000,000,000,000 electron volts, and that's the natural unit for the highest energies that we probe experimentally as of today. But a century ago, an MeV was the energy frontier, and Rutherford not only discovered the atomic nucleus, but many discoveries were made with energies that were more or less the same as the energy available to Rutherford. I'll give one other famous example from the early days. This involved naturally occurring particles with more or less the same energy as Rutherford's. But they did not come from radioactive sources in the lab. They were high-energy particles that reach us from outer space, called cosmic rays. If we had a detector in this room for particles that, in my line of work, are part of the bread and butter, called muons, you'd see that muons from space are passing through this room all the time, hundreds per second, I think, given the size of the room. So these particles are called cosmic rays, and one of the first big discoveries made using cosmic rays was the discovery of antimatter. So I'll show you a real picture on the next slide, but because the real picture is confusing, here I have a schematic picture. An electron in a magnetic field will spiral around, and this direction in which it spirals is determined by its electric charge. If you had a particle like the electron but with the opposite charge, it would spiral around backwards. I've tried to draw two spirals looking at the arrows, where one is going around left-handed and one right-handed. So this is the real picture that led to the Nobel Prize for C.D. Anderson. So what we're seeing is the track made by a cosmic ray passing through a photographic plate. And so take a look at this track here. So first of all, this particle is moving relativistically close to the speed of light. So we can't tell if it was going up or down by timing it with a clock. The times are much too little. But we see that the curvature gets sharper as it goes up. The particle is slowing down as it goes upward. And by looking at the direction in which it's bending, Anderson discovered that what he was finding was not an electron, but what we now call the antimatter equivalent of the electron, the positron. A particle like the electron, but with the opposite electric charge. So this was actually the discovery of antimatter. The most basic property of antimatter is that matter-antimatter pairs can be created and annihilated. In this picture, time is running horizontally, and what I'm sketching, the purple wiggly lines are meant to be photons. Physicists often, in drawing so-called Feynman diagrams, use wiggly lines to indicate photons. Here, two photons are annihilating into an electron-positron pair. So photons are as close to pure energy as it gets, and they can be converted to matter, that is, into antimatter-matter pairs. Similarly, electron-positron pairs can annihilate into photons. So if you travel to a distant solar system and meet a creature made of antimatter, it's not a good idea to shake hands. So antimatter was one of the strange discoveries of 20th century physics, but perhaps the strangest of all was quantum mechanics. In the quantum world, everything is a little fuzzy. If you know where a particle is, you don't know how fast it's moving. I've tried to indicate this with this picture here. So time runs vertically and space runs horizontally. The black curve, if you conceive of it classically, the black curve is the path of a point particle in space and time. At every time, indicated by the blue dotted line, or this one later on, the particle is somewhere. And as time evolves, it traces out a path in space-time. But that's a classical picture. Quantum mechanics tells us that a picture like that is inherently fuzzy. If you know where the particle is, you don't know which way it was moving, and you can measure where the particle ended up, but you'll never know how it got there. The quantum uncertainty principle is actually the reason that high energies are so important in physics. It implies that to discover small things, like an atomic nucleus, one requires a probe with high energy, like the radioactive beam used by Rutherford. So for Rutherford, high energy meant energy that was naturally available from radioactive sources, and that was high enough energy to discover the atomic nucleus. But to get the uncertainty principle means that to get farther, one needs higher energy still. So this is a picture of a contemporary detector, actually, that's made important discoveries with cosmic ray particles. Well, one of the relatively few fundamental discoveries in particle physics that really makes a splash in the general press came about 15 years ago when this detector discovered the mass of little particles called neutrinos. So I'm not sure if you see this very well. These are three physicists in a boat, and they're floating on extremely pure water. And a tank is being filled with this very pure water, and the walls of the tank are lined with these phototubes, which are being checked or repaired or something. And when it's all going, it's about 50 meters across. It's completely filled with these with water, extremely clear water, and photons created in the water by passing charged particles are detected by the phototubes on the walls of the tank. So this is a modern version of a cosmic ray detector. So, well, it's a specialized one. This was a very primitive cosmic ray detector in 1932. Here's an admittedly specialized, but still, it's a modern version of a cosmic ray detector, which well, actually made a Nobel Prize-winning discovery concerning neutrino masses. So we still do exciting things at modest energies, but because of the uncertainty principle, to get farther, physicists had to make artificial accelerators to reach even higher energies than nature provides us. So in accelerators, charged particles, usually electrons or protons, or their antiparticles, are accelerated using electromagnetic fields. So a simple example of a particle accelerator. So, like anything, this started with very simple ideas. And particle accelerators of circa 1930 used to exist in everybody's television set. The basic idea then was that there was a hot filament from which electrons would boil off, and there was an electrically charged plate with positive charges that would attract the electrons. And you could make a beam of electrons of relatively high energies that you could use to light up a spot on your TV set, or alternatively to do some interesting physics experiments. Then if you want to get farther, you have to be able to steer your beam. The simplest idea to do that is just a magnet. Actually, we discussed it before because we had the electron and the positron spiraling in opposite directions in a magnetic field. So once you can make a beam of electrons, you can steer it with magnets or electromagnets, then you can do better. And once you get started in this business, you find out that by using time-dependent electromagnetic fields, you can do better. And bit by bit, new techniques were developed. And as the energies got higher, people kept making interesting discoveries. And one thing led to another, and finally to the modern accelerators of today, which I'll describe in a moment. So by the 1960s, electron beams were available with an energy of a few GeV. I just remind you that a GeV is 1,000 times what Rutherford had. It's mc squared of a proton rather than mc squared of an electron. By smashing these beams into atomic nuclei, physicists repeated Rutherford's experiment at higher energies. Rutherford had discovered that the atom had a hard core, the nucleus, and was not just a mushy blob of jello or something. Now, it might seem surprising that the same story would be repeated at 1,000 times higher energy, but physicists of 1960 believed that a proton was a little blob of jelly. It wasn't quite as silly as it sounds, because lower energy electron scattering experiments made it look like the proton was a blob of jelly. But when the energies got to a few GeV, it turned out that although the proton is a blob of jelly, it contains hard bits, which we now call quarks. So the basic observation was the same as Rutherford's had been, but at higher energy. There were a lot more events at large scattering angles at very high energies than were expected if a proton was really a blob of jelly. So the modern picture which emerged from this and other experiments is that a proton or neutron is made of 3 quarks plus gluons that hold them together, where the quarks have fractional electric charges that add up to the charges we observe for the proton and neutron. Now, to go on, we want higher energies and also stronger beams, but because there's a limit to the fields that we can use to accelerate or steer the beams, to get to higher energies, we need a bigger accelerator. And that's why accelerators have kept growing in size and cost, leading up to the Tevatron in the US and the LHC in Europe. So the energy of the LHC is currently 4 TeV in each beam, where I just want to remind you that an MEV is Rutherford's energy, a GeV is the energy of the 60s, and a TeV is the energy of frontier experiments today. So Rutherford discovered the atomic nucleus at MEV energies, but to discover quarks and understand the nucleus took GeV energies. And to understand the mysterious weak force in nature has required the TeV energies that we're only reaching now. So the culmination so far of our study of the weak force has been the apparent discovery of the Higgs particle last year at CERN, which has been in the news about as much as a scientific discovery can be. So I'd like to tell you what the Higgs particle is all about. We all know about electromagnetism, but for the most part, only people who study physics learn about the weak interactions. So we all know about electromagnetism, even if not the name, because we detect electromagnetic effects with our eyes, light waves, and other electromagnetic effects are obvious in everyday life, including magnets, static electricity, and lightning, among others. But while electromagnetic effects are obvious in everyday life, it takes modern equipment to detect the existence of the weak interactions or study them. The most well-known manifestation of the weak interactions is in certain forms of atomic radioactivity. So basically, the radioactive decays that were the basis for Rutherford's beams were in part connected with weak interactions. So even though electromagnetism is obvious in everyday life, but it takes modern equipment to understand the weak interactions, our best understanding is that the two are described by the same type of equations. In fact, that's one of our most incisive insights about the unity of the most fundamental laws of nature. So, to a large extent, it was proved 30 years ago that magnetism and weak interactions are basically the same. A previous accelerator at CERN, a predecessor of the LHC, discovered the W and Z particles, which are the basic quanta of the weak force in the same sense that the photon is the unit of electromagnetism. And incidentally, this discovery was made with an energy of about 500 GeV. That means 100 times more than needed to discover quarks, and 1/16 of where we are currently. So according to the fundamental laws, the W and Z are no different from the photon, but we all see photons, and it took the accelerator to discover W's and Z's. Something hides two of them from our ordinary experience, and according to theory, that something is called symmetry breaking. So this picture is meant to suggest it symbolically. The little bowl at the top of the hill symbolizes the universe. The universe is about to roll down the hill because the top of the hill is unstable, and break the symmetry between the different forces. To be perfectly balanced on top of the hill is completely symmetrical, but it's unstable. The stable state is at the bottom and isn't symmetrical. So the little bowl will roll down the hill, breaking the symmetry in this case between the weak interactions and making the universe the way it is. When the ball gets to the bottom of the hill, it can vibrate there. That's what a real ball would do, of course. When it would get to the bottom, but then it could slosh around. And according to quantum mechanics, vibrations of a field are what we interpret as particles. In the case of the little ball or field that rolled down the hill and broke the symmetry between the forces, the vibrations are what we call the Higgs particle. So, to me, that's the most basic understanding of what the Higgs particle is. But I'm going to mention another interpretation, in part because it's also important, but also in part to make contact with what you may more often read. The side of the Higgs particle that's more often emphasized in popular articles is the following. Most of the particle masses arise when the ball rolls down the hill and breaks the symmetry between the forces. This goes for the W and Z masses, the electron mass, and the masses of the quarks. Well, the particle masses are a big deal in the scheme of things. For instance, if the electron didn't get a mass, it would fly away at the speed of light, rather than being bound into atoms and molecules. So we wouldn't have any atoms. We would have, well, we'd have a world made of the objects that particle physicists usually study, but not a good place to live in. So in short, the little ball rolling down the hill hid the weak interactions, left us to see light waves, made it possible for atoms to exist, and in brief, made the universe the way it is. So it's actually a very beautiful theory, and the theory was put forth by Weinberg, Glashow, and Slam in the 60s following earlier work by Higgs and others. And a lot of circumstantial evidence suggested it was right, and by now it's been decisively proved by the apparent discovery of the Higgs particle last year. But there's something about it that's bothered physicists ever since I was a graduate student. The particle masses are small. Well, what does that mean? Obviously, the mass of an electron is small by human standards, but that's perhaps more a statement about us than about electrons. For us to be big and complicated enough to be able to think about an electron, we're inevitably made of many, many atoms and molecules. So it's inevitable that the electron mass seems tiny to us. So the ratio of a human mass to an electron mass is as much a problem for biologists as physicists, probably. To a physicist, it seems more interesting to compare the electron mass to the constants of nature. And then we get a different sense in which the electron mass is small. The simplest way to make this comparison is to compare the gravitational force between two electrons to the electrical force between two electrons. The gravitational force depends on the mass, and the electrical force depends on the charge. So here we get the chance to see how big is the electron mass in units of fundamental natural constants like the electron charge. Gravity loses by a lot. It's way weaker even than the weak force. According to Newton, the gravitational force between two electrons is Newton's constant times the mass squared over the square of the distance. And Coulomb said that the electrical force is the same thing, but with the charge of the electron squared. So they both are what are called inverse square laws, but gravity is weaker by a factor of 10 to the 42. That's why you sometimes feel an electric shock from the doorknob, but you never feel the gravitational pull of the doorknob. All the atoms in the doorknob are exerting a gravitational pull on your hands, and the shock comes from a tiny fraction of the electrons in the doorknob. But the shock due to a tiny fraction of electrons is much, much stronger than the gravitational force due to all the electrons in atomic nuclei, because the particle masses are so small that you don't feel the gravitational force. So gravity is important, but it's important for big objects. For example, the Earth. The Earth is made of something like 10 to the 52 elementary particles, and yes, when you put that many of them together, gravity builds up. Electricity didn't build up for the Earth because it's almost electrically neutral. For every electron, there's a proton, to very, very good precision. But at the atomic level, gravity is incredibly weak. Particle physicists have put a huge effort into theories that try to explain why the little dip in the hat is so shallow, and hence why the particle masses are so little. So this picture is not drawn to scale. If that picture were drawn to scale, then the gravitational force would not be much weaker than other forces, than the electric force. The gravitational force being so weak means that this is an incredibly shallow little dip in the hat. So to physicists of my generation, well, we practically grew up on this like mother's milk. It's the hierarchy problem, as we called it. And it seemed obvious it must have a rational explanation. All kinds of ingenious proposals have been put forward. Some have already run into trouble. Others are still viable and will be tested in the next few years as we learn more about the Higgs particle and about what happens at LHC energies. One of the still viable explanations is something called supersymmetry, to which many colleagues and I have devoted a lot of effort. Roughly speaking, supersymmetry is an updating of Einstein's special relativity in the light of quantum theory. According to supersymmetry, beyond the obvious dimensions of space and time, there's an additional quantum dimension. If supersymmetry is correct, one doesn't measure space-time just by numbers. It's now 3 o'clock, we're 200 meters above sea level, and so on. There also are quantum variables that you need to use to describe space-time. So, in such a world, an ordinary particle like the electron could vibrate in the quantum dimension, and that would be observed as a new particle, electrically charged but spinless and non-magnetic, unlike the electron, which has spin. It could be produced and detected at the LHC. So roughly speaking, if we would find super partners, the zoo of elementary particles would double, as it did when antimatter was discovered in 1932. So back in the 20s and 30s, we learned that the electron is two-valued quantum mechanically. It spins like a tiny magnet that can be up or down. Unfortunately, it would take another lecture to properly understand that, because the spin of the electron can't be visualized classically. It's a kind of infinitesimal quantum variable itself. And as I told you before, the electron has an antimatter cousin, the positron, that also has magnetic properties, but its electric charge is opposite. If supersymmetry is correct, the electron has yet another cousin that we would hope to discover, which is spinless and hence non-magnetic. Supersymmetric particles have not been discovered yet. And it's a bit of an embarrassment, certainly for some versions of the theory where it should have happened. But there's a possible hint of supersymmetry in data that we already have, which involves measuring the strengths of the different forces of nature and extrapolating how they change as the energy is increased. This plot summarizes a vast amount of experimental data. What's plotted, gravity isn't on the plot because gravity is too weak to be seen in the same units as the other forces. But the three particle physics, the three stronger forces, the weak electromagnetic and stronger nuclear force are shown here. And their strength is plotted on the vertical axis. The horizontal axis is the logarithm of the energy. And the plot is made by starting with measurements at relatively low energies and making a theoretical extrapolation to high energies. When you make this extrapolation, there's an energy where the three curves meet, as if all the forces of nature were getting unified at that energy. So it's not any two curves you might hope to meet, but for three curves to meet at the same point is a little bit exceptional. And the fact that it does occur here has been interpreted by physicists as a hint of a deeper unification of the laws of nature than we have really established experimentally. But this extrapolation is made using supersymmetry. So the fact that the extrapolation works is also a hint of supersymmetry. So hopefully, the meeting of the three curves is an indication of supersymmetry and of some deeper unification of the laws of nature, and not just a misleading coincidence. And hopefully we'll know within a few years. Well, one question is, why do the curves meet as if supersymmetry is real if we haven't seen supersymmetric particles yet? One suggestion has been something called split supersymmetry, according to which what we would hope to see at the LHC are the partners of the photon, the W and Z particles, and the Higgs particle, but not some of the others. Supersymmetry, even in a partial version like that, would imply the first real change in the way we think about space-time since Einstein. Einstein's concepts of space and time were entirely pre-quantum mechanical. It hardly could have been different because quantum mechanics was in the future when relativity theory was invented. In fact, Einstein helped lay the seeds of quantum theory at the same time as he was developing relativity theory. But the quantum theory didn't come to fruition until later. Finding supersymmetry would force us to at least begin to include quantum variables in the way we think about space and time. But it might potentially help with something even bigger, which has to do with the title of my talk. So I've tried today to convey the fact that physics became very strange in the 20th century. So moving clocks slow down, particles are waves, energy can convert into matter. Almost all these strange things are everyday facts of life if you work with elementary particles. But there's one exception. There's one of the strange facets of 20th century physics that hasn't been melded with the particle theories. That's Einstein's greatest achievement, which is his theory of gravity. According to Einstein, gravity results from the curvature of space and time. So the sun, think of this as the sun, and that's a planet. To Newton, the planet goes around the sun because it's attracted to the sun. To Einstein, the sun causes the space-time around it to be curved. The planet is trying to go in a straight line in a curved space. A rough analogy is a trampoline, where you put a ball on the trampoline, and then you put a marble on the trampoline. If you think about it, the marble could circle around the central ball. It looks like it's being attracted and kept in orbit, but what's really happening is that the trampoline is curved. The ball doesn't know it's being attracted to the marble, but locally, the way the trampoline is curved will cause the path of the ball to curve. So Einstein reinterpreted the motion of the planets in terms of the curvature of space-time. Now, I explained that we don't see gravity from the doorknob, but of course, gravity eventually becomes important when masses are big. So gravity is mostly studied by astronomers. By the way, that's a picture of the Andromeda galaxy, which is the most distant object ordinarily that you can see with the naked eye, but not from New York City, I don't think. From Wyoming or someplace, if you know where to look, you can see it with the naked eye. There's a problem with gravity, which is that the nonlinear mathematics that Einstein used are not compatible with the quantum field theory that were used to describe elementary particles and their forces. So in practice, modern physics is based on quantum theory for atoms, while general relativity is used for stars, galaxies, and the whole universe. It's hard to combine the two theories. Something's wrong with this, since stars and galaxies are ultimately made out of atoms. They all have to be described by the same theory. And experience has taught us that we should take seriously problems like this one. But I think that this problem would simply have looked too difficult to me, and I would never have tried to work on it personally, had not an interesting approach fallen out of the sky. Or more accurately, it emerged as a lucky byproduct when physicists were trying to do something else in the late 60s and early 70s, before I was in the field, incidentally. The one real idea about combining quantum mechanics with general relativity is string theory. So, to say it in the simplest way, in string theory you replace a point particle by a little loop of string. Except you have to remember that both the particle and the string obey quantum laws, which make them a little bit fuzzy, which I haven't tried to draw because you can't do justice to it in a picture, really. Well, this point is really an extended object just so you can see it. But it's hard in a picture to convey the way a point particle becomes fuzzy because of the uncertainty principle. And for the string, it's only harder to explain. Like a violin string, one of these strings can vibrate in many ways. So a violin string is held down at the two ends, and one of these strings is just a loop that is freely floating in space. But they still share the property that they can vibrate in many different shapes, which in the case of music correspond to the fundamental tone and the higher overtones, which are responsible for the richness of music. And if string theory is right, it's responsible for the unity of the elementary particles, with all the different elementary particles arising as different forms of vibration of one basic string. It sounds like an incredibly naive idea. It has incredibly far-reaching consequences, which I should try to explain in about 5 minutes. So I'll resort to a picture. So this is a picture describing what's happening in space and time. Time runs horizontally and space runs vertically. And actually the picture is a picture of a Feynman graph. The one on the left, the green one, is what Feynman, well, Feynman didn't call them Feynman graph. It was perhaps Richard Feynman's single most famous innovation, and other physicists called them Feynman graphs. So a Feynman graph you can think of, Feynman did think of it, as a history of particles in space and time. So one particle is shown as coming in the past along this line. The line gives the orbit of the particle in space and time. And then at the moment x, this particle broke into two particles. One of them recombines at the event y with another incoming particle. So the picture on the left is a history where two particles came in the past and two went out in the future. But in between, there were various events where one particle broke into two, or two recombined into one. So that happened at special space-time events that I labeled X, Y, Z, and W in the picture. And we need special rules for what happens there, because those were special events where something did happen, and Feynman invented those rules. So after Feynman, when physicists are describing standard quantum field theories, part of what they do is to explain what are the rules at these interaction events. However, there are many possible theories because there are many different possible rules for what happens at X, Y, Z, and W, and also many choices for what kind of particles are represented by the green lines. And finally, there's trouble because quantum mechanics tells us that all X, Y, and Z, and W are possible. To use the jargon, we have to integrate over X, Y, Z, and W. And when we do that integral, we run into trouble when they all coincide. Those lead to the so-called ultraviolet divergences of quantum field theory, which were tamed by Feynman and his contemporaries, including Freeman Dyson, who I understand gave one of these lectures here last year. But although they were tamed, it's always been a source of trouble, and it actually does not work in the case of gravity. I should better say that these problems were tamed for the non-gravitational forces. For the string, things are different because there's no special moment. I've drawn here a close-up of the previous two pictures. So, first of all, here on the right is a stringy version of this picture. Each line has been replaced by a tube, representing the path followed not by a point, but by a loop of string in space-time. And instead of the particle breaking into two, a string breaks into two. But the difference is that a string can break into two smoothly. To explain it better, I've given a blow-up here. Now time runs vertically, so in this, on the left, one particle came in and broke into two at a moment x. On the string theory side, I can draw the same picture, but everything is completely smooth. Any moment of this diagram, if you look at it under a magnifying glass, looks like any other. So this has a number of consequences. One is that for the string, space-time becomes fuzzy. You see, in the conventional picture, there was a definite space-time event. And that was a prototype of the fact that space-time has a sharp meaning, which is very similar to the way Einstein understood space-time. What are happening in space-time are quantum phenomena, but the space-time itself isn't changed. But in the string theory, there's no definite moment where something happens. Sometimes people ask me if there isn't a last time where there was one string instead of two. The answer to that is that it depends on the observer. Einstein tells us that the laws of nature are the same for different observers moving with different velocities. And different observers would disagree on what was the last moment where there was one string instead of two. So really, in the string theory picture, there's no distinguished moment, and that's the beginning of the fact that space-time becomes fuzzy. There's no definite moment of a notion of a space-time event. Space-time exists on the average, but if you look closely, it's not there. The string embodies new ideas in geometry that we don't yet understand. Another fact is that the string makes its own rules. In the particle picture, the particle comes along and then Richard Feynman or somebody decided what are the rules where one particle breaks into two. But when the string breaks into two, there's no place where any new rule is needed. The string makes its own rules. It generates its own interactions. String theory has a mind of its own, and it does what it wants, irrespective of the wishes of the physicists studying it. So, historically, out popped quantum gravity, whether you like it or not, and the people who first discovered it didn't like it. They were trying to describe the strong interactions, not quantum gravity. They kept getting equations that described a massless spin 2 particle. That was completely wrong for the problem they were trying to solve. Eventually, somebody pointed out that it wasn't so bad because it was what was needed to make sense out of quantum gravity. Out popped gauge symmetry, which I didn't really explain tonight, but it's the bread and butter of the standard model of particle physics. I said that the W and Z and the electromagnetism were all described by the same basic laws. Those are laws of gauge symmetry. And another thing that people didn't like originally, they regarded it as a joke, is that out popped 10 dimensions of spacetime. No one was looking for extra dimensions, but physicists studying string theory had no choice but to learn to live with them. Nowadays, we see them as a blessing in disguise. If you're going to do string theory, you have to interpret all the particles as different states of vibration of one basic string. And since there are an awful lot of known particles, many different kinds of quarks, the photon, the neutrinos, the W and Z, the Higgs particle, since there are a lot of different particles, it can be a tall order to interpret them all as different ways that one basic string can vibrate. So having the extra dimensions gives us room to do that. That's a modern view on the meaning of the extra dimensions. The last piece that pops out is supersymmetry, and this may be the piece that we have the best chance to test in the foreseeable future. Hopefully at the LHC. So I'll conclude by hoping for good news in the coming years.
Thank you, Edward. We're going to open it up for a few questions, and Bridget will come and give you the mic so that we can hear you. Who has a question, if you've strung along with everything?
It's always a simple question from a non-expert. Do you have some exciting plan for your new or latest award of $3 million, which to a layperson seems pretty good source of some good things?
It's difficult to think of a gracious way to answer that, and I've had trouble.
In the back, right there, gentlemen.
Hand up.
Hello. Given the first data sets of the 7 and 8 TeV data
Yes.
from LHC and the energy increase to 14 TeV, what are your personal outlooks on how supersymmetry is doing as far as the experimental outlook goes?
Personally, I think that from where we are now, natural explanations of the weak scale are under a lot of pressure. The reason people usually phrase that question in terms of supersymmetry is that others have been in even more pressure for longer, like composite Higgs particles. Supersymmetry has worked better until now, and natural explanations are still conceivable. But the reason I mentioned, well, there's a very naive reason to think that one might want to take split supersymmetry seriously. It is that the main success of supersymmetry, I'm assuming from the way the question was phrased that you want a more detailed answer than the rest of the talk. The main success of supersymmetry has to do with these scalars. Has to do with the fermions, which are important in making the renormalization work. And the phenomenological problems have to do with the scalars. So split supersymmetry moves the scalars up to where they don't cause any harm. The problem with it is that even if the basic idea is right, it's unclear if 13 or 14 TeV is enough for the fermions. And the same goes with other attempts to try to discover it. For example, the neutron electric dipole moment should be relatively close at hand. But whether it makes a world of difference whether relatively close means it's 1 order of magnitude or 2 orders of magnitude.
Professor Kaku?
About the multiverse problem, if there are many, many solutions of string theory, is there any hope that we'll find the unique solution that describes our universe, or maybe we simply coexist with billions and millions of other universes? What are your thoughts?
I don't have any really clever ideas to offer, unfortunately. I hope that something nice will happen that will make it possible to understand more clearly if string theory is correct. And I don't have a clear picture of how that would happen. Yes?
Was gravity at one point strong and maybe over the years it got weak? And what weakens gravity, and will it ever be strong? I never heard of weak gravity before.
Well, I mean, there are various possible answers. So there was a famous proposal that was made more than half a century ago by Paul Dirac, who also was the one who predicted antimatter, although I didn't explain that in the talk. So I mentioned the number 10 to the 42 in the talk, but there's a very funny coincidence, which is that if you measure the age of the universe in units of the time it takes a photon to cross an atomic nucleus, you get 10 to the 42 again, more or less. I might have that slightly wrong, but it's something a lot like that. And that led, okay, so see, one of them depended on the age of the universe and the other didn't. So it seems like we're living at a lucky period where that's true. Well, Dirac said maybe this relation is always true, but if so, gravity's getting weaker in time. So Dirac's idea was that gravity is so weak because the universe is so old, to state it briefly. However, since his day, technology is far better, and we now know that the rate at which gravity is changing is much too small for Dirac's idea to be correct if taken literally. There are some more modern ideas that are roughly along the lines of what you've asked. They're very speculative.
Gentleman in the center there, and then the other gentleman.
How far do you think are we from an understanding that would allow us to at least formulate a Gedanken experiment that if it gave a certain result, you would for sure say that string theory is false? I mean, in the falsifiability picture of science.
Well, the falsifiability picture of science is a little narrow. A lot of what scientists do has to do with either discovering things or confirming theories. So the Higgs particle was discovered, which you can describe as by saying that the standard model wasn't falsified. But most people who think of it, most of the people who actually did it thought they were searching for the Higgs particle. So therefore I'm not going to answer your question quite literally. The best answer I can give, which I think is in the spirit of an answer to your question, but it's not an answer for precisely the way you phrased the question, is that the role of supersymmetry in string theory is part of how supersymmetry was discovered. And supersymmetry is very important in the structure of string theory. So the discovery of supersymmetry would be a strong hint that one's on the right track. Wouldn't be a proof that you're on the right track. But I would suspect that if supersymmetry were confirmed, you wouldn't find a lot of people in physics departments claiming that string theory was useless. That's just a personal suspicion.
The gentleman right there, and then
Steven Weinberg, in the New York Review of Books last spring, perhaps, bemoaned the lack of funding for the future of big science, and also the fact that the super collider wasn't built in Texas. And I'm curious, twofold. What is your opinion of the future of funding for big science? And is the LHC at CERN going to give the kind of results that physicists are going to want? And for how long into the future? And at a certain point, will they absolutely need something much more powerful, and what are the possibilities of ever achieving something like that?
Well, first of all, the Higgs particle already was a big discovery. We've wondered about it for 40 years, since the early genesis of the theory. And in any event, the LHC has made that discovery, and it's doing a fantastic job of greatly increasing our understanding of what happens at the so-called TeV energy scale. As I told you, I'll give a detailed answer in the question, but I want to say a few general remarks first. As I mentioned during the lecture, my generation of physicists grew up with the belief that at TeV energies, there has to be a rational explanation for why the particle masses are so little. We're finally reaching TeV energies, and it's conceivable that that belief is being falsified. There's still hope that that isn't what's happening, but it might be. So that's a nod to the last questioner who thought that science has to do with falsification. So the view that there should be a rational explanation of the weak scale is definitely testable at LHC energies and is under some stress now. And it's anybody's guess what the LHC will discover at 13 or 14 DV. I think that there's decent grounds to hope that at 13 or 14 DV, the LHC will discover physics beyond the standard model, maybe some of the super partners, maybe something that we don't anticipate now. And I think if there is physics beyond the standard model, but probably only a partial picture of it, there will be a strong case for going on beyond the LHC. Will people go on? I can't promise we will, but I think we will. I think if there is a strong case, if we begin to see a picture beyond the standard model that we're not able to explore completely at the energies we have at the LHC, I think people will want to go on, and the case will be strong enough that some country will decide to do it. It would be nice if it's the US, but can't make any promises there. Maybe it'll happen in China.
gentleman in the back.
What does string theory have to say about dark matter and dark energy, if anything?
Well, I'm going to give an answer that doesn't require the whole machinery of string theory. I'll just give an answer in the context of supersymmetry. And I'll even put it in a slightly more general context also. Supersymmetry suggests the existence of what are called WIMPs, weakly interacting massive particles, with masses by E equals mc squared. Their masses correspond roughly to LHC energies. And people look for them in underground facilities of various kinds. You can either say that they're searching for WIMPs or that they're trying to falsify the hypothesis that WIMPs exist. Now, supersymmetry suggests WIMPs, but there's also something else that has suggested WIMPs to a lot of physicists for the last 30 years, really. It has to do with the theoretical calculation of how much dark matter there would be, starting from a hot, dense, early universe. And it turns out that a calculation based on WIMPs works pretty well at reproducing what we see. With that said, the WIMPs haven't shown up yet, and the WIMP searches keep improving. They've got a ways to go, but you know, it's like super partners. They might have showed up already.
Are there any more questions? Otherwise, I want to thank Professor Witten for this very nice class. Thank you all for coming. On March 6th, I believe, Sheldon Glashow will be here, who is a friend of Ed's, but has a different perspective. Pardon me, yes. We will be selling some of the textbooks that Edward Witten wrote with two colleagues in the back. There are refreshments for everyone. And once again, I want to thank the Simons Foundation for having encouraged us and underwritten this series of talks. Thank you all for coming.